One of the world's heaviest trains currently weighs over 44,000 tons. Yet this enormous weight rests entirely on two steel rails with a contact surface only about 3 inches wide. How can such a small strip of steel withstand continuous extreme pressure for years without deforming or breaking? The answer lies in an extremely special manufacturing process with stringent technical standards. In today's video, we'll delve into the details of how these extraordinary load-bearing rails are produced. Today, the global steel industry is worth over $1 trillion annually. Yet, only a tiny fraction, less than 1% of the world's steel, is used to produce railway tracks. The steel rail manufacturing market alone is currently worth approximately $15 billion. Interestingly, this crucial material didn't start with steel at all. The earliest rails in history were actually made of wood. Around the 16th century, European mines used parallel wooden planks to help mine carts move more easily. Later, they began reinforcing them with cast iron to increase durability. However, cast iron was too brittle and frequently cracked under the increasing loads of the first steam locomotives. This limitation spurred the development of steel rails. But what's even more remarkable is that while materials, manufacturing technology, and train speeds have changed dramatically over the past 2 centuries, the fundamental principle of the modern railway system has remained virtually unchanged. In 1789, British engineer William Jessop perfected the design using grooved wheels running on 2 flat-end rails. More than 200 years later, from freight trains carrying tens of thousands of tons to modern high-speed trains, the majority of the world's railway systems still operate on that same principle. The journey of a railway track begins in massive iron ore mines deep underground. Many open-pit mines span dozens of square miles, where large hydraulic excavators and super-heavy dump trucks operate continuously day and night. Some modern excavators can lift up to 67 short tons of ore and rock in a single bucket. Before the ore is brought to the surface, engineers must drill holes more than 100 feet deep into the bedrock. These holes are then filled with industrial explosives and detonated in a precisely calculated sequence. The goal is to break up thousands of short tons of rock with each blast while preserving the quality of the ore inside. A single large explosion can release the equivalent of tens of tons of TNT, but it is carefully controlled to ensure the rock fractures precisely as planned. In some areas, ore is also extracted from underground mines with a network of sturdy tunnels deep beneath the surface. Although machines handle much of the heavy lifting, humans still play a central role in designing explosions, operating equipment, monitoring safety, and checking the quality of the ore before it moves on to the next stage. After being extracted from the mine, iron ore is not immediately usable. It must undergo a crushing process to achieve the appropriate size for steelmaking. In modern plants, giant jaw crushers can process from 3,000 to over 10,000 short tons of ore per hour. Next, the ore is passed through additional crushing and screening systems to reduce its size to about 1/4 of an inch, equivalent to small gravel or coarse sand. This size is very tightly controlled. Once it meets the standard, the ore is blended with coke and limestone in large industrial mixers. Heavy mixing blades weighing tens of thousands of pounds continuously rotate to distribute the materials evenly. Only when the composition is precisely controlled from this stage can the finished steel achieve the necessary strength to withstand the weight of massive trains for decades. After being crushed and blended, iron ore enters the most crucial stage of the entire process, steelmaking. Inside the plants, massive blast furnaces and electric arc furnaces operate at temperatures exceeding 2,900 degrees Fahrenheit, enough to transform the raw material into homogeneous molten steel. Automated control systems continuously meter the material, while sensors and analyzers monitor temperature and chemical composition in near real time. During this stage, elements such as manganese and chromium are added in precise proportions to increase the steel's hardness, wear resistance, and load-bearing capacity. The scale of this process is far greater than many realize. A modern electric arc furnace can melt more than 165 short tons of steel in less than an hour. However, the steel industry is also one of the world's largest sources of industrial emissions, producing approximately 7 to 9% of global carbon dioxide emissions annually. After leaving the furnace, the molten steel is cast into ingots and transferred directly to the holding area. The steel billets are not immediately rolled but must undergo a heat treatment and preparation phase. They are transferred to giant reheat furnaces, where the temperature is maintained between 2,200 and 2,400 degrees Fahrenheit. Depending on the size of the billet, this process can last from 1 to 3 hours to ensure even heat distribution from the outer shell to the core of the steel. If the temperature difference between areas is too large, the billet may crack or deform under pressure in the next stage. Once the required temperature is reached, the billets are removed from the furnace using an automated roller conveyor system hundreds of feet long. Along the way, they pass infrared temperature sensors, surveillance cameras, and most notably, a high-pressure water spray system that removes the oxide layer formed during the heating process. When leaving the heating area, the steel billets are fed straight into the rolling forming line. This is the process of turning solid steel blocks weighing dozens of short tons into long rails with precise shapes. First, the billet passes through roughing rolling racks, where giant alloy steel rolling rolls press and stretch the metal. Each time it passes through a set of rolling rolls, the cross-sectional area of the workpiece decreases while the length increases significantly. Next are the intermediate and finished rolling presses. A modern rail production line typically uses from 10 to more than 20 consecutive rolling racks, each of which only changes the shape of the steel slightly. Instead of being pressed into shape at once, the metal is shaped step by step to avoid internal defects and help the material withstand pressure better. Through each rolling process, the rail head, rail body, and rail foot gradually appear clearly, creating the characteristic shape of the railway rail. Interestingly, this design has a thick rail head at the top, a relatively thin body in the middle, and a wide rail foot at the bottom, making it look quite like an I-section. This structure helps the rail achieve high rigidity while still significantly saving on the amount of steel used. After being formed, the rails remain at very high temperatures and contain significant internal stresses within the metal. To stabilize the structure, they are passed through a cooling system hundreds of feet long. High-pressure nozzles continuously spray the surface with water or a fine mist, lowering the temperature to around 200 to 300 degrees Fahrenheit. If cooling is too rapid or uneven, the rails can warp or develop small cracks. Depending on the manufacturing standard, many factories also apply additional heat treatment processes to increase hardness and wear resistance. This step ensures the rails can withstand millions of train wheels rolling over them over decades of use while maintaining the necessary shape and durability. After the heat treatment process is complete, the rails are moved to the welding area to form continuous long rail sections. Here, a roller system precisely positions the two ends of the rails before they are joined together. Under the influence of extremely high temperatures and strong pressure, the metal at the joint melts and fuses into a single block. Any excess material generated during welding is immediately cut and ground away to ensure a smooth surface. The entire process is tightly controlled to ensure that the weld has the same strength and load-bearing capacity as the original steel of the rail. The finished rails are then transferred to the quality control area. Here, industrial cameras and high-speed optical scanners inspect the entire surface to detect even the smallest scratches, deformations, or dimensional deviations. Simultaneously, ultrasonic testing machines emit sound waves through the metal to search for hidden defects such as cracks or voids invisible to the naked eye. Some samples are also subjected to mechanical tests to assess hardness, strength, and load-bearing capacity. All results are stored in a data system for traceability. Only rails that pass all inspection standards are accepted for packaging and shipping. After leaving the factory, the rails are transported to the construction site by oversized trailers. Many modern rails are up to 300 feet long and weigh over 13,000 pounds, so they must be secured with specialized support systems and chains to prevent deformation during transport over hundreds of miles. Upon arrival, hydraulic cranes and large lifting equipment lower each rail into the staging area. From there, installation begins. Based on the design drawings, the construction team uses laser levels and surveying instruments to precisely position each rail according to the correct elevation and alignment. Initial joints are temporarily secured before being welded or permanently tightened. Although machinery handles the lifting of components weighing thousands of pounds, much of the project's accuracy still depends on human experience. Workers constantly coordinate with each other to adjust the spacing, straightness, and position of each rail. Even a small deviation can affect the operational quality of the entire railway line. It is this meticulous attention to detail in the final stage that helps create stable, safe tracks capable of continuous service for decades. From ore deposits deep underground to rail tracks stretching thousands of miles, the rail manufacturing process is a combination of mining, metallurgy, precision engineering, and centuries of technical expertise. Each rail track undergoes countless stages, from ore crushing and steelmaking to rolling, heat treatment, and rigorous quality control, before being deemed ready for use. If you found this journey interesting, please like the video, share in the comments what topic you'd like us to explore next, and don't forget to subscribe to the Mido Explained channel to not miss the fascinating stories behind the familiar objects that power the world every day.